In this problem, we have two identical pendulums of length L hanging side by side from a common support point, and their bobs having a mass m just touching, and then an equal charge q is placed on each bob. Now, obviously, what happens when these two bobs acquire some charge, which is identical, we expect them to repel, and that's what has happened here. And we can directly actually draw the electric force of repulsion on each of the two bobs. We were told that the bobs have a mass m, so since we're studying forces, maybe it's useful to see that we have some weight forces as well. We want to find an equation relating theta, the angle each pendulum string makes with the vertical as shown in the figure, to the other parameters given in this problem. So this angle theta is actually due to the repulsive force, and our pendulums are going to just establish equilibrium at this angle theta. So this angle theta is basically the angle at which our tension force is able to balance the electric force and the weight force on each bob. So we can actually immediately think of equilibrium then in order to study the situation that we have here. Now, in any problem that is involving forces, we have some steps that we need to address. We start by drawing the forces or making a free body diagram. So I have already drawn the weight force, the electric force. We still have one more force, which is the tension exerted by the string of our pendulum. I think studying both bobs will just give the same results, so I'm just going to address the left pendulum. Both will give us the same equations. Our second step for studying forces is to find x and y components of each of the forces. So I will start by drawing my x and y axes, and then finding the components of each of the forces that we have. So I'll start with the easy ones. The electric force, its x component is actually in the negative side of the x-axis, so that's minus Fe. Its y component is 0 because it's along the x-axis. For the weight force, it's the other way around. The x component of the weight force is 0, and the y component of the weight force is minus the weight itself, because again the weight force is in the negative part of the y-axis as well. For the tension force, this is an oblique force, so it will have both x and y components which are non-zero. So you can see how Tx is actually the quantity that we have here. This is Tx, and it actually depends on the angle theta that T makes with the x-axis, right? This is T cosine. I'll call this theta prime just to check if it's the same as theta that is given here. So if we actually consider this triangle here, we can see that the angle here, which I labeled as theta prime, is not actually the same as this one. In fact, theta prime is equal to 90 minus theta. So if I would like to write this in terms of theta, which is the given in this question, I'll have to write this as 90 minus theta. And this is actually the same as sine theta. And for Ty, I will have T sine theta prime, which is T sine 90 minus theta, which is T cosine theta. So these are my x and y components. And then the third step for studying a problem involving forces is to apply Newton's law, or to find the net force if I'm not sure which Newton's law I have to study here. However, I know here that I have equilibrium. So when I apply Newton's law here, I can just apply Newton's first law because I know we have equilibrium. So I can simply say that sigma fx is equal to 0 and sigma fy is equal to 0. By sigma fx, I mean the sum of all of the x components of all of the forces acting on the bob. Now, what are the x components of the different forces? I have the x component of the electric force, the x component of the weight, and the x component of the tension. And the same thing here for the y components. For the x component of the electric force, I will have minus Fe. For the weight, we got 0, and for Tx, we got T sine theta. So our first equation gives us that t sine theta equals Fe. For our second equation, we have 0 minus W plus t cosine theta equals 0. So we just got that t cosine theta equals W. Now we can actually write the expressions of the electric force and the weight force as well, so that we get some new expressions. For the electric force, the expression is k q squared over r squared. I put q squared because q1 and q2 are equal to each other. And here I have t cosine theta equals to mg. Now I can divide these two equations to get rid of the tension force. This will give me that tangent theta equals k q squared over mg r squared. Now m is a quantity that is given in this problem because they asked us to find theta in terms of the parameters given in the problem. In this problem, we're given the mass m, we're given the charge q, and the length L of the pendulums. So m is given, q is given, r is not a quantity that is given. Instead, we are given the length L of the pendulum. However, we can directly link r, which is the separation between the two charges, to the length of the pendulum that is given here. So if we address the same triangle as before, this one, we can see that sine theta is equal to opposite over hypotenuse. The opposite here is r over 2, and the hypotenuse is L, which is the length of the pendulum. So we can get a relationship between r and L. So r is going to be 2L sine theta. So you can directly substitute this here. For L squared sine squared theta. So if we are given the situation of very small angles, which makes sense for electric forces because usually they have very small magnitudes, so we expect our bobs to barely get lifted from their equilibrium position. In this situation, sine theta equals tangent theta, and these two can be approximated by theta itself. So then we can rearrange the equation. We will have tangent theta times sine squared theta equal kq squared over mg 4L squared, which gives us theta times theta squared equals kq squared over mg 4L squared, which means that I can actually just rewrite this as theta cubed. So theta is going to be the cubic square root of kq squared over mg 4L squared.